propose to go ahead for the next talk. So from Professor Angélique Rissons, who is professor at the ISAE-Supaero in France, and she will present photonics for free space communications. Give you the floor.
So, hello everyone, I'm Angélique Rissons, donc I'm professor at Institut Supérieur of Aeronautic and Space in France, Toulouse, so in the south of France, and I'm responsible of the team Photonics, Antenna, Microwave and Plasma in the Department of Electronics, Optronics and Signal, DIOS. So my presentation, my talk is about the free space optics communication. So it's not exactly the energy, direct energy transport, but we are working on the transmission of data through the atmosphere between satellite and ground station. So I will introduce the free space optics through the context of this kind of link. And also I will present the breakthrough of this kind of link. And after I will present you how to achieve the emulation, the modelization and the emulation in lab of the free space optics link. So the context is well known, is digital divide, and this digital divide has been increased this last few months, especially due to the crisis of COVID, and also the development of the telecommuting, especially for the work and also for the health and for the education. So that's why today, more than previous months, the increase of bandwidth is very important. So now we have two main challenge is to compare the network, the ground network, especially the fiber optics networks, with the satellite network. So today the satellite network is mainly in a radio frequency band, but the radio frequency band is limited as we encountered before the 19th, because of the copper cable were limited, and the solution has been in 19th the deployment of fiber optics network, especially the long haul network, transatlantic network, for example, and transcontinental network. Since 19th, we assist of the deployment of several other networks, especially the local area network, the fiber to the homes, etc., and the deployment and hybridation of the fiber optics with the radio frequency network. There is also any other networks which has been deployed. It was the optical wireless between building or into building, especially with the Wi-Fi today. If we compare that, the ground network, with the satellite network. So the satellite network is composed of several different satellite orbit, especially with different network and different applications. For example, we have the geo orbit at the high altitude, several thousand, so more than 30,000 of kilometers altitude. The medium Earth orbit, 20,000 kilometer altitude and less, and the LEO orbit, 400 kilometer altitude. So we know that the geostationary satellite is in fixed position. The MEO satellite have an orbital period of between 2 to 24 hours around the Earth, and the LEO orbit have a few 10 minutes orbit around the Earth. So that's why there is different applications. The geostationary orbit satellite is for the TV or internet, is close to the intercontinental link. For example, the transatlantic link, it could be compared with the transatlantic link, the transatlantic optical fiber optic link. So this is the same application. For the MEO orbit, it's mainly for the navigation, for the GPS, GNSS, Galileo, etc. And the LEO orbit is mainly for the phone or for the telemeasurement and imagery. So today there is a new constellation in deployment, especially the Starlink satellite constellation, where with the SpaceX, various SpaceX lift off. In fact, SpaceX deployed more than 10,000 satellites to cover all the Earth for the phone communication, phone and smartphone communication. And it's in balance with the geo-satellite communication, which could replace the fiber optics between components. So if we look at timetable of the deployment of the free space optics communication, in fact, the free space optics communications has been in the beginning of 2000th century, especially with the first link between geo-satellite and LEO satellite. So before having a ground satellite link, we had inter-satellite link between Artemis, the geo-satellite, and Spot 4 satellite, LEO satellite. The second step was to do any link between geo-satellite and aircraft, high altitude aircraft. By this first try of link, it has been demonstrated the possibility of communication over a few megabit per second up to several gigabit per second and more. The first generation used the wavelengths of 850 nanometers laser. The second generation used higher wavelength of 1 micron 64, and it was due to the technology available for the space application. There is also different format of detection. For example, the first generation used the direct detection, and the second one used the coherent detection. Different waveform also, modulation format. For example, for the first generation, it was amplitude modulation, OOK, on-off keying. And for the second generation, it was phase shift keying modulation. Currently, we are studying the 155 nanometers link between LEO Earth and GEO Earth satellite. The challenge still to have a high power, to use the laser, the high power laser embedded into a satellite with high stability in terms of divergence, in terms of relative intensity noise, in terms also of chirp and line width. So this is a challenge for the terminals, for the emitter, for the transmitters. There is also some challenge on the detection format, also the use of preamplifier, the use also of adaptive optics. So this is a timetable of the free space optics. So we can see that there were some first demonstration. The first demonstration with the SILEX project is still in orbit, and after the LOLA project in 2006, and etc. And today there is a lot of mission planned for several liftoffs. So this is the evolution of the bit rate. So this representative, this curve is not really representative because we have to take into account of the context of the mission. We have to take into account also the altitude of the platform, and also we have to take into account the reliabilities of the platform. Well, our project is a collaborative project in Toulouse with different industrial and academic projects. For example, we are in partnership with Airbus Defence and Space, Thales Alenia Space, the French Space Center, and the Institute of Research of Technology of Toulouse. We are working on, first of all, on the feasibility. We are working on the feasibility of the link, of such a link. And the feasibility was mainly at the beginning to take into account of the breakthrough. The first breakthrough was the cloud lockage. So the cloud lockage is an important phenomenon. It's important because it cuts the availability of the link. So we studied how to have any program of ground station and any possibility to change the link with the ground station network. The second breakthrough is to study the turbulence, atmospheric turbulence, and to do a beamforming. And also the other breakthrough was to have available technology of terminals at the wavelengths of 155 microns. The data speed also. We have also to take any trade-off, to have a trade-off between adaptive optics and the detection, and also the bit rate, and also the use of error correcting code. And at the end, in concurrent engineering, we have to take into account also the availability of terminals in satellite platform. So regarding to the effect of temperature, effect of vibration during the liftoff, and also effects of the radiation on the fiber optics. So here it's more detail regarding this breakthrough study. So the turbulence, I will present our emulator after. The nebulosity, there is any nebulosity prediction to plan to do any bifurcation on the ground station. We have also to study the terminals availability, the terminals architecture, and also the waveform adapted to all the canal, all the communication chain. So this is an example of chain. So this is our first hypothesis, our first study in physical layer simulator by using a MATLAB simulator, and also by use co-simulation with other software, for example, VPI Photonics. So, and homemade simulator on Pythons. So we take into account of the data, the frame coding, and the possibility of parallelizing interleaving. We input that on the Mach-Zehnder modulator, and we take into account the multiplexing, wavelength division multiplexing. We have a booster amplifier EDFA, erbium.fiber amplifier, to reach the target power. We take into account the atmospheric propagation channel, especially different various attenuation possibilities, and also the turbulence, the atmospheric turbulence. We take into account various scenarios of adaptive optics, so different loop of adaptive optics. A low noise optical amplifier, it's a pre-amplifier before injected before coupling the flux into photodetector. So between the adaptive optics, we have to couple the flux, the light flux, into the fiber optics, into the single mount fiber optics, and after we have to go to the detection multiplexing, and after the optoelectronic demodulation. So the challenge is to ensure the coupling of the telescope detection with the single mode fiber coupling. So I will detail that after. So this slide presents why we are too interested to the 155 microns wavelengths instead of 1 microns wavelengths or 800 nanometers wavelengths, because of, first of all, the atmospheric transmission as these wavelengths at 155 microns. Second one, the available technologies, especially which has been developed and make their proof in the fiber optics communication due to the minimum of spectral attenuation, and also the high safety. Our approach is in a term of concurrent engineering, that is to say, we are working with the upper layer research, especially the network layer, especially the computer science, and also we are working with the people who develop the astronomic system for adaptive optics, and also we are working with the device manufacturer to give them the constraint, the requirement of the space mission and the effect of the space environment on the satellite platform. So now, regarding the problem of the cloud impact. So as I previously introduced, the cloud lock the link, especially for the cloud with higher thickness than the cirrus. So we have to consider the meteorologic cloud mask data band to predict the availability of our link. So we introduce into a simulation tools this Meteosat data bank, and we found the solution of developing a satellite backbone by taking into account the cloud lockage. If each ground station are connected by a backbone, optical fiber optics backbone, in fact, the availability of the link through continents, for example, for the Europe, is close to 100%. So if we are able to predict the nebulosity several milliseconds before the link, we are able to have an availability of 100%. The second step is the knowledge and the prediction of the phenomenon of turbulence, of atmospheric turbulence. So the atmospheric turbulence, as it has been presented before, is involve degradations of our beam profile. Instead of having a spot, a laser beam homogeneous, we have some effect in the detection. We have different various effects. For example, we have beam wandering or beam spreading. So it change, it make moving our laser beam, or it make enlarge it. And also at into the laser beam, we have phenomena of scintillation, such as the speckle phenomenon, which is well known in sensing. So these effects are due to the vortex of the wind. So the wind is mainly due to the effects of the change of the wind and the temperature variation between the troposphere and the stratosphere. So at this altitude, close to 11 kilometers, 11 kilometers, we have a tropopause. So the atmospheric turbulence, as well known in aeronautics science, but in optical science is well known for the astronomy. So in astronomy, they use the adaptive optics, and they did some measurements which help us to develop, which allow to develop the evolution, the statistical model of the refractive index according to the altitude. So this is the turbulence. This is the turbulence coefficient. This coefficient is connected to the variance, to the standard deviation of the refractive index, and it allows us to predict the evolution, the variation of the amplitude according to the link, according to the altitude of the link. So it allows us to do a model of the fading of the amplitude. So if we represent this effect of atmospheric will be transposed into the detection, because once the wavefront of the beam is detected by the telescope at the plane of the pupils, we focalize it into the single mode fiber, and also we could lose some information, and we could change some information on the detection. So the solution, which has been developed during any PhD, the PhD of Lucien Canuet with my colleagues of Onera Dota, and also my other colleagues of the computing science, we try to find the best trade-off between the optical adaptatives and the communication link. In fact, the adaptive optics, is any loop which makes the correction of the wavefronts into a deformable mirror. So, at the pupils of the telescope, at the detector, we have a tip tilt mirror, and we detect the wavefronts. And by using a computer, by using a wavefront sensor, we applied a deformation in the mirror. And after, we could detect a correct image. So, but the problem of this loop, of this correction loop, is this loop is very, very slow instead of the communication beam. So according to this loop, once we correct the information, we lose a lot of sample of packets of data. So we have to find the best trade-off between the optical adaptatives and the solution of correcting code. Else, regarding the terminals. So the terminals, we studied different various kind of terminals by using various kind of waveform for the modulation. So for the moment, we have some results. I'm able to present some results with two kinds of modulation. The on-off keying modulation with avalanche photodiode detection and preamplifier and PIN photodetection. And also the DPSK optical modulation, so the dual phase phase shift keying with preamplification, PIN detection with balance photodetector. So it has been developed during a PhD of Karim El Ayoubi. So this is the architecture of the scheme of this modulation. So we have data, we have Mach-Zehnder modulation on the data, we have the head-phase booster, we have the channel, atmospheric channel, and also we have the detection. So it could appear very simple regarding the telecommunication, the ground telecommunication and fiber telecommunication point of view. But if we consider the free space optics, we have to take into account the influence of, first of all, different kind of aided noise, not only due to the head-phase ambient doped amplifier and the photodetector amplifier, but also due to the channel. We have also taken into account the coupling of the flux into the amplifier also. So that's why it's still a challenge. So we studied different architecture, another one. So that's why we have to compare different kind of modulation format and find the best way to find the best compromise between the modulation format and the correction of the noise and also the compensation of the atmospheric fading and losses. So the other architecture is the DPSK architecture. So we have the close to the same emitter, but the difference is also obviously on the detection. We have to use the delay line, interferometer delay line, and balance photodetector. So that's why we are able to compare both possibilities of modulation. But the problem is to do any achievement of this. So I think I spent too much time. Oh, it's okay. I didn't take into account. So I have to continue by the emulation. So in fact, we deployed in our lab the emulation of the satellite link. So we deployed two emulators. We deployed a fiber optics emulator with a transmitter, channel, and receiver. This fiber optics emulator takes into account only the effect of atmosphere by fading, by attenuation. And we are developing an emulator, a free emulator, free space emulator by using any degradation, any holographic system, and by using a DMD system to be able to know what happened on the phase of the beam and how to reproduce the atmospheric turbulence and the effect of the atmospheric turbulence on the beam. So we use this model and we applied that to DMD distributed the device micromirror, and we are able to do any holographic system, and we have any representation of the effect of the turbulence according to different scenarios and on the beam. Okay, so I think I have to finish and to be quick. So we developed with the fiber optics emulator this kind of emulation, and we obtained some experimental validation, which allow us to test different kind of terminals before putting these terminals, embedded these terminals on a satellite platform. And we compare various kind of modulation format on NRZ OK or with various duty cycle. And we are also able to compare the precompensation with or without adaptive optics, and also with different scenarios of turbulence effect. So I have to conclude because I'm looking at the time. So today we could say that the free space optics between satellite and ground station is still a challenge, because we have different solutions to compensate the effect of atmospheric turbulence, but this solution, mainly based on adaptive optics, limits bit rate. So we cannot reach 1 terabit per second bit rates with adaptive optics. We are also we are developing we are improving the turbulence emulator, especially the free space emulator, because it could be used not only for the free space optic communication, but also for the LiDAR application. For the power beaming, it could be interesting also, but we have to introduce the effect of the atmospheric absorption. And we are working on the current detection. So thank you for your attention. And if we have a couple time of question.
Thank you very much, Angélique Rissons. So some questions. We don't have any questions. I have one question. I have one question. So regarding the deformable mirror, the wavefront correction, what is typical requested correction speed?
So in fact, it depends of the link, but we. For the moment, we are looking to less than a few milliseconds, because we lose a lot of packets if we increase the bit rate up to 10, above 10 gigabit per second. We lose too much packets.
Okay. Thank you very much for your answer.
Welcome.
Thank you very much for your interesting talk.